Hello, my name is Michael Worosz, and I will be doing my presentation on iron. We'll start with the history of iron. It is relatively believed that the first humans to discover iron discovered it before the year 5000 BC, and that they discovered it from meteorites rather than digging it out of the earth. We assume this because we know that Mesopotamia, which is the earliest known civilization, was already smelting iron, and Mesopotamia existed around the year 5000 BC. Although we don't know when exactly the Iron Age began, it is relatively accepted that in between the years 1300 and 1200 BC, the Iron Age took place. And the Iron Age was essentially when all the civilizations, which at the time were using bronze materials and bronze tools, converted to iron materials and iron tools, because iron was officially cheaper than bronze. For the mechanical properties for iron, on the left you will notice two graphs. The one on top is the tensile stress-strain curve, and the one below is the compression stress-strain curve, both for iron. Iron has an elastic modulus of 200 gigapascals and a shear modulus of 77.5 gigapascals. When you compare this to other metals, it is relatively average. Iron has a yield strength of 50 megapascals and a tensile strength of 540 megapascals. These are relatively low values when you compare it to a material like steel, which is one of iron's alloys in which carbon is added. Iron has a density of 7.87 grams per cubic centimeter and a ductility of 0.55, meaning that it's not very ductile when compared to metals such as copper or aluminum. Iron has a toughness of 150 megapascal meters to the 1/2, and under all the hardness tests, these are the results. The Brunel test has a result of 146, the Vickers 150, the Rockwell A 49, and the Rockwell B a 79. In terms of crystal structure and atomic level, iron has the BCC crystal structure, otherwise known as the body-centered cubic crystal structure. There's a picture of the BCC crystal structure in the top right of this slide. This is where there is one single atom in the center of the crystal structure, surrounded by atoms on each corner of the crystal structure. Because of this, there's a total of 2 atoms per unit cell, and that is because there is the one atom in the center, counting for one total atom. And if you add up the total of each atom on the corners of the crystal structure, it'll add up to one more total atom, for a total of 2 atoms per unit cell. Also, iron has an APF, or atomic packing factor, of 0.68, considering that it has the body-centered cubic crystal structure. Iron's primary bonding is metallic bonding, considering that it is a metal. Iron has a melting temperature of 1,510 degrees Celsius, which converts to 2,750 degrees Fahrenheit. Iron's atomic radius is 0.126 nanometers. If you look, the other image on the slide is a scanning electron microscope image of iron. Iron's crystal structure has an edge length of 287,645 times 10 to the negative 8 centimeters. In terms of the environment, iron can lead to acid mine draining. There was a study conducted by the Wisconsin Department of Natural Resources, and it discovered that sulfide materials are exposed to air and waste, which can produce sulfuric acid in the water surrounding an open pit iron mine. The mine in this slide is an open pit iron mine. Also, with open pit iron mining, it can lead to a large depletion of water in the surrounding area, that of wetlands, lakes, and streams. This happens because an open pit iron mine is essentially a hydraulic sink in which when rainwater comes in, it'll leak through the cracks of the bedrock, ultimately draining surrounding wetlands, lakes, and streams. In 2016, the global emissions for iron was roughly 28.8 kilograms of carbon dioxide per megaton, which is relatively low when compared to the extraction of other materials out of the Earth's surface. However, the water usage was 1,950 megameters cubed per ton, which was very high when compared to other materials extraction. And this makes sense considering the large amount of water damage that iron mining does to the surrounding area. In terms of failure, iron has a brittle fracture. It is not a very ductile material. It has very little change in cross-sectional area, and its crack propagation is very fast. This is important to note considering that it's very hard to see a brittle fracture coming due to these factors. Iron is also very susceptible to fatigue failure. This is another very important thing to note, especially with how much iron is used in vehicles, such as a car, for example. There's going to be a lot of fatigue happening to certain parts of that car, so the fatigue failure of iron needs to be well understood so that it does not occur. Corrosion is probably the most common failure with iron. As you can see in this image, is an image of a rusted up truck. Rust is what happens when iron corrodes. It is essentially when oxidation and reduction reactions occur throughout the entire material surface randomly at the microscopic level. Once this happens, it will turn iron or its steel alloy into rust. And this is very important to note considering that rust is a lot weaker and a lot more brittle than both iron and its alloys. So this is important to consider when creating a machine with iron. Iron still has a lot of current uses in today's society. For example, iron is still used in audio systems, motors, toys, medical equipment, computers, wind turbines, instruments, sporting goods, industrial machinery, transportation equipment, cell phones, and magnets. Thank you for listening to my presentation on iron.